right, everybody. Hello. Welcome back. This will actually be our last lesson that we do by remote learning. So what we're going to be talking about today is a little bit of a continuation from last time. Last time we started talking about conservation of energy, the idea that the energy that you start with and the energy that you end with are equal. Will not gain or lose energy. It can change form, so we can change from kinetic to potential or back. We can change form, but no matter where we put our energy, whether it's kinetic or potential, the total will always stay the same. So we're going to keep talking about that, and really all that's going to happen is we're going to take that same idea. There's going to be a little bit more math involved, and I'll explain all the details as we go. So here we go. So I want to review a few things here really quick. Energy is the ability to do work, or that just means that it can cause a change in another object. Total energy is conserved, as I mentioned. So in each problem, the total energy stays the same from beginning to end. And as I said, energy can change form, so potential to kinetic and back. Even if we include friction, that was something we explored last week a little bit as well. Even if we include friction, the total energy does not change. Like a skater going up and down the ramp, they will slow down and eventually stop, but that energy isn't just gone. Friction converts it from kinetic energy into thermal energy. So anytime you've got friction, it'll take some of that energy and turn it into heat, basically. That's what thermal energy is, right? If you take your hands and you rub them together for a very long time, your hands start to get warm. Friction makes heat. Okay, so then we've got our two equations that we've talked about. The kinetic energy equation, Ke for kinetic energy equals 1/2 times mv squared. Mass is for velocity. We measure that in kilograms. M is for mass. We measure that in kilograms. V is for velocity. We measure that in meters per second. And then we had our gravitational potential energy equation. GPE equals mgh. All multiplied together. M for mass again. G is the acceleration due to gravity. That's our friendly 9.8 that we always use as long as we're on Earth. And then you've got h. H is for height. How far from the ground are they for h? Okay, so example 1. So I've kind of lined these examples up. This first example is going to be one where you have to use an equation before you deal with the energy. And example 2 will be where you use the equation at the end. So here we go. A 5 kilogram box is released from the top of a ramp that is 12 meters tall. How much kinetic energy does it have at a point partway down the ramp where it still has 100 joules of its potential energy? And for this one, we're going to ignore friction, pretend it's not there. Okay, so it's released from the top of a ramp. It's not thrown down the ramp, so it isn't moving to start with. And if it's not moving to start with, then it has no kinetic energy, which is 0. So we can find the total energy using just the potential energy that it starts with. So we need our potential energy equation, mgh, and then we plug in our m, our g, and our h. M, our mass, is 5 kilograms up here. First thing it says, 5 kilogram box, so that's our mass. G is our 9.8, as usual, as long as we're on Earth. And h is 12, because it says that the ramp is 12 meters tall. Okay, so then we just multiply those together, and you get 588 joules. Boom, there you go. We're almost done. So because there's no kinetic energy to start with, the potential 588, that's the same thing as the total, because we didn't have any kinetic energy to start with. It was sitting still to start with. So at the beginning, the potential energy and the total energy are the same then. Okay, so partway down the ramp, if it still has 100 joules of potential energy, that means it must have 488 joules of kinetic energy. And how did I do that? At the end, we still should have a total of 588. Of that 588, 100 is in potential, so we just subtract. That's all I had to do. Take the total, 588, minus 100, because 100 is potential. So what's left over is 488 for the kinetic. Okay, so this is an example where you have to use an equation at the beginning before you can answer the energy question. Okay, and you kind of know this stuff based on what are they telling you at the beginning. At the beginning, are they, for the beginning of the problem, when it starts at the top of the ramp, are they talking about energy, or are they talking about measurements like height? So you can always tell based on what are they telling you about the beginning of the problem. Okay. So example 2, this is going to be one where we need to use an equation at the end. So example 2 is a 0.15 kilogram baseball thrown up into the air with 50 joules of kinetic energy. So we take a baseball and we're throwing it up into the air. It's got 50 joules of kinetic energy. What is the velocity of the ball when it has 35 joules of potential energy? So what we want to do is we want to assume that the ball starts from a height of 0, and once again we're going to ignore friction, keep things a little bit simple right here. We're going to totally ignore friction. Okay, so if it starts with a height of 0, then that means its potential energy is 0. So we can figure out the total by just using the kinetic energy that it started with. That's 50 joules. So 50 joules of kinetic energy, there's no potential, so that means the total energy is also 50. So that means to figure out the velocity, first we need to figure out how much kinetic energy is left. So it started with 50. We transformed 35 of that 50 into potential energy. So how much is left? It started with 50, but 35 of that is now changed to potential. So how much is left? There's 15 joules of kinetic energy left. So now that we know how much kinetic energy it has when it's up in the air, then we just need the kinetic energy equation to figure out the velocity. And here's that kinetic energy equation again, Ke equals 1/2 mv squared. Okay, and then we're just going to plug in all the numbers that we got. For the energy, we're going to use the 15, because it had 50 to start with, but now we've only got 15 left. 35 went to potential. And then, as usual, I changed my 1/2 to a 0.5. It's just easier to deal with the calculator that way. M is 0.15, because at the beginning they told us the mass. That's kilograms, 0.15 kg, kilograms. So that's how we know its mass, is that kg. And then V is the only letter left. That's what we're trying to figure out. Okay, so the first thing that I'm going to do is multiply the 0.5 and the 0.15 just to get one number there, 0.075. Everything else stayed the same. 15 is the same, V squared is the same. All I did was multiply the 0.5 times 0.15. Now to get V by itself, first we have to get V squared by itself. So let's divide these numbers. 15 divided by 0.075. And when you divide that, that's 200. Okay, but that's not the velocity. That's the velocity squared. So we have one more step to do. We don't want V squared. I want normal V. So we got to take the square root at the very end here. V equals the square root of 200, and that's 14.1 meters per second. Okay, 14.1 meters per second. So this is our final answer here. Okay, so once again, how did I know that the equation we needed was at the end? It's because they started with talking about energy. We knew the energy to start with, and then they told us a little bit more about energy. 35 changed over to potential, and so we know if it's a whole bunch of energy in the problem and they're not really telling you how the height or the velocity, that's when you know you're going to need the equation at the end. Okay, example 3, I got one more example, and this one right here, and then after this we're going to break down kind of a bigger problem, because you're going to see something similar to it on your test. I want to make sure that I give you an example of something like that, just to make sure we don't have any troubles. But one more example first. Okay, here we go. A 50 kilogram skater has a velocity of 8 meters per second, so we're probably going to need to use that in the kinetic energy equation. Okay, so this 50 kilogram skater has a velocity of 8 meters per second as they roll through the bottom of a half pipe. And it wants to know how far up the ramp is the skater when they have 200 joules of kinetic energy left and 100 joules have been lost to friction. Okay, so first of all, they gave us the velocity, so we're probably going to have to use that in the kinetic energy equation. They're asking how far up the ramp, so we're looking for a height. So this is going to be a problem where, based on what they told us with the velocity and what they're asking for height, we're actually going to have to use both of those equations, the potential energy one and the kinetic energy one, one at the beginning, one at the end. So this is kind of putting the first two examples and using them both in one problem. And we have friction this time. We lost 100 joules to friction. Don't freak out about that too much. It's actually pretty easy to deal with that. Okay, so the first thing, they start with a height of 0 because it tells us how fast he's going as he rolls through the bottom of the half pipe, right? So if he's at the bottom of the half pipe, there's no height. And so if his height is 0, then he has no potential energy. zero potential energy. So we can figure out the total energy by just looking at his kinetic energy. Okay, so we need our kinetic energy equation. We're just going to plug in this time, and everything, we know all the stuff on the right side, which is nice. So 1/2 changes to a 0.5, like I always like to do to make calculator stuff easy. Our mass is 50. It says at the beginning a 50 kg skater. Kg is kilograms. That's how we know it's mass. So that goes in the M spot for mass. And his velocity is 8 meters per second. So that goes in the V spot. You got to remember to square the 8. You're not squaring everything, just the 8. Okay, so when you put all that in your calculator, you should get 1,600 joules. Okay, and so like we said, he didn't have any potential energy when this problem started, as he's at the bottom of the half pipe. So that means the kinetic energy and the total energy at the beginning of the problem are the same. Okay, so his total is 1,600 joules. All right, so now we need to know how much of that is going to be in potential. Okay, so 1,600 is the total. We're going to take away 200 because 200, it says, is still in kinetic energy. And we also got to take away another 100 for the friction. Okay, so all we're doing is taking the total and subtracting out the other two pieces, 200 for kinetic, 100 for friction. That's all you got to do to deal with friction. It's just going to be an extra minus, a number in there somewhere. Okay, so you do this 1,600 minus 200 minus 100, and you get 1,300 joules. That's how much potential we have when he's partway up the ramp. Okay, so now all we got to do is use the potential energy equation to figure out the height. Now we know how much potential energy he has. We're going to use that equation to get the height. So here's our potential energy equation, equals mgh. We know that he's got 1,300 joules of potential energy. That's what we just figured out right there. We already recognize that the mass is 50. G is our 9.8, as it usually is. And then we've got H. H is what we're trying to figure out. Okay, so first thing I'm going to do is do 50 times 9.8. So now that's 490. Everything else stayed the same. H is still H. 1,300 is still 1,300. All I did was multiply these two numbers right here, and that's 490. Now to get H by itself, we're almost done. One step left. We just got to divide, and we've got H by itself. H is 1,300 divided by 490, and when you do that, you should get 2.65 meters. Okay, so we had to use one equation at the beginning, and it's not always going to be the kinetic energy equation that you have to use at the beginning. You might have to use the potential energy at the beginning and use the kinetic at the end, or maybe use kinetic both times, or maybe use potential energy both times. It just depends on the problem. But just trying to give you an example of something where you're going to need a equation, one of them at the beginning, and use another one of them at the end as well. Okay, so what I want to do now is go through an analysis of a roller coaster. The scenario for this problem is a child is excited to play with his new model roller coaster kit. He is building an ejector coaster that matches the drawing shown. He likes a challenge and wants the roller coaster to come to a safe stop at the end, up on the top of the hill. Find all missing values. So all these blanks, we got to fill in all of these blanks right here. The mass of the coaster is 5 kilograms, and it leaves the station with a velocity of 24 meters per second. Okay, so the first thing that we want to recognize is that at the bottom, it's at point A, it's starting on the ground, right? It's starting at the very, very ground, and so that's 0 joules. Okay, 0 joules. All right, and it also ends, when it ends at the top, it says he likes a challenge and wants the roller coaster to come to a safe stop at the end. So that tells us that we can put a 0 somewhere else. This time at the end, because it's not moving, we can put a 0 by the kinetic energy at the top, because it should stop, which means it's not moving, and the kinetic energy is 0. Okay, so those are the easy ones to fill in. If it's at the bottom, a roller coaster is at the bottom, it should be 0 for potential, and if it's stopped anywhere, it should be 0 for kinetic. All right. So we also were told how fast it leaves the station. So it's 24 meters per second. So we can figure out, and we know the mass too. It's 5 kilograms. We know M and we know V. So we can figure out the kinetic energy that it starts with. And the kinetic energy that starts with, okay, we've got our 1/2 changing to 0.5. Our mass is 5 kilograms, 5 kg, that's our mass. And it says that the velocity is 24. So we put 24 squared right there. So multiply all this together, you should get 1,440 joules. So I'm just going to go ahead and put that in its spot right here. 1,440 joules, kinetic energy at point A. Now notice, if the potential energy is 0, then when you add these together, it doesn't change. It's 1,440. So that's our total. So I'm going to go ahead and put that in our total spot over here at the end. 1,440 joules. That's our total. Okay. But at the end, we have one more blank that we can fill in really easy here, because at the end, if we're not moving and KE is 0, well, that means P, the potential energy, is the same thing as the total, 1,440. And so there you go. Just one equation, and we have been able to fill in 5 blanks already just from one equation. And we didn't even need the equation for the zeros. We only really needed it for the 1,440. Okay. All right. So now we've got some information. We got to do point B and point C. Really not too bad. At point B, we know the velocity, so we can just use the kinetic energy equation again. Kinetic energy is 1/2 mv squared. Just going to plug everything in. 1/2 is a 0.5. M is the same M it was before. The mass doesn't change. It's the same roller coaster. So 5 goes in the M spot. This time it's only going 18 meters per second. So that's what goes in our V spot. Multiply all that together, and we've got 810 joules. So I'm going to go ahead and put that 810 in its blank spot up here, 810 joules. And now to figure out the potential energy, it's really not too bad. We know the total is 1,440, and how much of that goes to kinetic? It's 810. So to figure out how much is left over for the potential energy, you just got to subtract. The total is 1,440. Take away 810, because that's the kinetic part, and how much is left? 630. 630, so that's going to go right up here in the potential energy spot, 630 joules. Okay, so now we've got all of point B figured out. Now we just need to do point C. It's going to be somewhat similar. We just need the other equation, right? Because at point C, they didn't tell us the velocity. They told us the height is 9 meters. That's okay. That's good. We have an equation that we can use that in. It's not the kinetic energy equation. If we know the height and the mass, we know M and we know H, we can figure out the potential energy then. Okay, so right here, where it's going to be pretty similar. We're just going to plug in. M is the same 5 it has been this whole time in this problem. G is 9.8 because we're on Earth. And H, they said right here, the height is 9 meters. So 9 goes in the H spot. 5 times 9.8 times 9, you multiply all that, and you get 441 joules. Okay, 441 joules. So that's going to go up here in the potential energy spot for point C, 441 joules. Very good. And to figure out the kinetic energy now we just got to subtract 1,440 minus 441, because that's the potential energy piece. And how much is left over for kinetic? 999 joules. I guess I forgot to put the answer in this spot. It's up here though. If you subtract 1,440 minus 441, get 999 joules. Okay, so we have filled in everything. It wasn't too bad, really. We had to use 3 equations, and we had to subtract twice. Really not too bad. Okay, should be able to fill all that stuff in. All right, that one is yours. You'll see that on your homework. But that's it for me. I don't need to go through anything else. I do want to go back and point out. Let's look at points B and C. I had to go through this problem, make sure all the numbers were going to work out, because what has to happen is the roller coaster is lower at point C, right? So if it's lower at point C, that means it should have less potential energy. Does it? 441 to 630? Yes, it's got less potential energy at point C. Okay, and so the higher you are, or the farther from the ground you are, the more potential energy you have, and that's it. And then because it's going back and forth from potential to kinetic, if you look from point B to C, the potential energy went down, right? Well, okay, if the potential energy goes down, what has to happen to the kinetic energy? The kinetic energy has to go up, right? because the total can never change. So if one goes down, the other one has to go up because they always have to add up to the same thing. And in this problem, that would be 1,440 joules. Okay, so likely there will also be something where, without even numbers, you should be able to compare what's the points on the roller coaster. Okay, even without numbers, you should be able to compare and say, okay, D has the most potential energy because it's the highest up in the air. B is next because it's the next highest up in the air. C is next because it's the next highest up in the air, and A has the lowest because it's below all the other points. Specifically, it's on the ground, but more importantly, it's lower than all the other spots. All right. So I got some decent response on that survey for doing a review session. So we're going to go ahead and do that. I'm looking a little bit later today at what time that's going to be. So make sure you're checking Google Classroom because I'll be posting about what time that video conference review session will be. Okay. But good news is this is the last lesson. So get this homework knocked out. We'll get you ready for the test next week. Take that and you're done. And then that's at least for my class, right? And then you're right there. Summer's right there. Hopefully everybody can get some time to relax, right? All right, everybody, stay positive. Look forward to seeing some of you on the video conference review call. And till next time, take care.